Hi, welcome to lesson 2D, special number sets. Over the past couple of days, we've looked at sets and Venn diagrams. So we're going to see where special number sets fit into those sets and Venn diagrams. So we're going to learn about, which you've probably already learned a little bit about these, and discern between base number sets. So here's a few of the more popular and well, all the number sets we'll be using in this course. So n is the natural numbers, or the counting numbers. In some places, this would be like perhaps called W, like the whole number system, starting at 0, and in other sources, n, the natural numbers, would just start with 1. But in our text, n includes the 0 and is then the counting numbers up from there. Z is the symbol for the integers, and integers are all the natural numbers, but also the negatives of those as well. So it's 0 and including plus or minus all of the counting numbers. Z positive is the set of all positive integers. So of course, if you had the Z negative, you would see that would be all the set of all negative integers. Q is the set of all rational numbers, and the numbers that can be formed. So rational numbers are in the form of P over Q, where P and Q are both integers, and Q cannot equal 0. So here's a few examples of rational numbers. So numbers that are integers that form fractions. So 3 over 8, of course, would be a rational number. Negative 7 over 5 is also rational. Because, of course, rational numbers can be negative because integers can be negative. Negative 3 2/3 is rational because we can rewrite that as an improper fraction from this mixed number form. And so we get negative 11 over 3. That would be the P over Q here. 0.3 repeated is rational, as 0.3 comes from 3 over 9 or 1 over 3. And, of course, 1 over 3 is that ratio of integers. And root 16 is also rational because root 16 can be written as just 4, and 4 we know is a rational number because it can be written as 4 over 1. Basically, all decimals that terminate, like for example 0.25 as one example, or recur. So it could be like this one up here, we saw 0.333, or it could be 0.6666, etc. Just written as 0.6 repeated. It could also be something like 0.714, 714, that sort of idea where they just repeat. And the fact that the value in the ones place keeps being 0 in my examples does not mean that those are the only types of rational numbers. But any sort of recurring decimal like that is also a rational number. Q prime or Q complement. So we talked about sets and their complement sets a lesson or two ago. Q complement is a set of irrational numbers. And those are numbers that cannot be written in rational form. And so, of course, we know that rational form mean that they are integers that are written in a fraction, P over Q. So irrational numbers cannot be written like that. So an example of irrational numbers would be root 3 or pi, for example. These are also ones that do not terminate or they do not recur. Okay, so there's no repeating decimals in there. So pi, one of the more famous numbers that does not repeat and does not terminate. Root 3 is also another one of those. Root 2 is also another one. Perhaps root 5, root 7, a few of these other ones cannot be written as a fraction with a ratio of integers. R is a set of real numbers, and basically real numbers are all numbers that can be placed on the number line. Includes both the union, so we talked about union before, the union of rationals and irrationals. So the irrationals and the rationals do not, intersect, those two sets, or subsets, I mean. So there would be Q and Q complement. So those don't intersect because rational numbers cannot be irrational and vice versa. However, the real number system is the union of those two. And actually, I should probably, if I was doing that, I should probably do it more like this. Just separate them into two halves of the real number system. Okay, because in this first diagram that I just drew, there would be something in the outside here, outside those circles. Okay, so I'm not going to use that to depict the union of rationals and irrationals. It would be more like a segmented universal space like this. 0 over 1 is irrational. It's not real. Of course, it's undefined because we can't divide by 0. And things like negative root 2, well, we can't have a square root of a negative value. So that also cannot be placed on a number line, and therefore it is also not real. Okay, let's take a look at the diagram. Here's a huge Venn diagram to visualize all of the different number sets. So in the universal set, it's basically made up of all complex numbers. The whole thing is all complex numbers. So this is the universal set of all number sets. And maybe that should be a capital U. I'm not sure if it really matters, but I'll just put capital here. And so we just talked about the real numbers, and the real number set is all the natural numbers. So here's the n for the natural numbers, and that's all the values 1, 1, 2, 3, 4, etc. The whole numbers 0, 1, 2, 3, etc. But for our purposes in our textbook, we'll be using this whole where the whole numbers is. That'll be the natural numbers for us. The integers, that's written with a Z. If I can draw that Z properly. Not really. Rational numbers are represented by Q. Irrational are Q complement. So it shows all the different number sets that we just talked about. The real number system, we use the R for that. And so notice in the complex number system, here is the C, we notice that all complex numbers are written in this form A plus BI. And real numbers are also written in that same form where B actually equals 0. So then that second part of the complex numbers, that just disappears. So we're just left with the A value, which is a real number. Okay, irrational numbers, root 2, pi, e, etc. Those are all just that A value. There's no plus BI there. And same with all the other rational integers, etc. Everything is complex numbers. Real numbers, like I just said, has the B equals 0. And here, the I is actually imaginary numbers. And so that's the where imaginary numbers is where we can say I, that I in this complex numbers is actually equal to the square root of -1. Okay, that's what I actually equals. And then you can play around with it from there. So an imaginary number would be some value, like some real number. So the real number would be here first. So some real number plus some kind of imaginary number. Okay, some coefficient multiplied by the root of -1. Pure imaginary numbers is where that A value at the beginning, the A plus BI, the A equals 0. So you're just left with the BI. So it'd be some sort of coefficient in front of the square root of -1. Okay, so these are all the just how all these values are working, all the different number sets. We're only going to be dealing with the real numbers in this course. We're not going to be dealing with the complex numbers at all. You'll get to that sometime later in your post-secondary education. Let's take a look to see whether each of these statements are true or false. -7 is an element of the positive integers. Well, it's not positive, so I would have to say that is false. B, 2/3 is an element of the integers. Well, 2/3 is an element of the rational numbers, but rational numbers are not integers. So that is, of course, true because we're saying 2/3 is not an element of the integers. So that is, oops, I'll write that perhaps in a different color. So the statement above is true. The square root or negative square root of 4 is a member of the integers. Well, root 4, well, we know that root 4 is just equal to 2. So, and -2 is a part of the integers, is a member of the integers. So that statement is true. Root 3 is an element of the rational numbers. Well, root 3 is irrational. So therefore, root 3 is not an element of the rational number system, and therefore that statement above is false. Uh, 7/9 is an element of the rational number system. Well, 7 and 9 are both integers. Therefore, and that's the definition of rational numbers, so therefore that statement is true. 0.201 is an element of the integers. Well, no, that's not true at all. And I think because that ends, there's no recurring there, or it doesn't seem to be any value. Was 0.201 can actually be written as 201 thousandths. And those are both integers. Therefore, that is a rational number. So therefore, the statement above that those are, that's an integer is false. We see that 7/0.31, at first view, it looks like we've got an integer over a decimal, but that decimal is can be a rational number. So we could actually write this if we were just to multiply top and bottom by 100. We can see that that could be written as 7/31, and that indeed is rational because the numerator and denominator are both integers. So that statement is true, even though it appears not to be at first glance. And for part H, we've got the modulus of -1, and the modulus is just telling us the distance of -1 from 0, and the modulus is +1, and so the square root of 1 is just 1, and therefore that is indeed a member of the real number system, so that statement is also true. Okay, so here's a little bit of work for you to digest all this. So thanks for watching, and we'll see you in class.